Hey guys, welcome to week two, welcome to lesson two of this week. Today we are going to be looking at limiting and excess reagents. So for the good news of you that really love stoichiometry last lesson, this is just going to be kind of picking up where we left off. And the bad news for those of you that struggle with stoichiometry, if you're still having a really hard time with it, please make sure that you've tried your homework questions before you start this lesson, because it's going to be really important that you understand the basics of stoichiometry. So let's start with an introduction of what a limiting and an excess reagent might be. All right, so we are going to start by talking about the grilled cheese. Last lesson, it was a chocolate chip cookie. Now it's a grilled cheese. Maybe I'm just really hungry in quarantine. But here we're going to talk about how to build the perfect grilled cheese sandwich. So the perfect grilled cheese sandwich is going to be 2 slices of bread for every slice of cheese, right? So you got to make sure if it's a real sandwich, you got to have bread on the outside and bread on the other side and cheese in the middle. So this can actually help us to understand what an excess and a limiting reagent is. Because if we want to make a proper grilled cheese sandwich, we can say that our chemical formula would be this: 2 breads for every amount of cheese that you need. That's going to allow us to make as many sandwiches that we want. So here's your problem. You might not have the perfect ratio. So let's say in your house you have 100 slices of bread. You're really hungry. You really like grilled cheese sandwiches. Let's say that you have 100 slices of bread and you only have 30 slices of cheese. The idea is you're going to run out of one of these before the other, right? You're only going to have so much bread or so much cheese to make a set number of grilled cheese sandwiches. I don't know if you guys have ever run into this before, but sometimes I'll buy a pack of hamburgers. Let's say that there's 8 burgers in the box, and let's say that there's only 6 buns. That means that I'm going to have leftover burgers. In this case, I'm actually going to have leftover bread, right? I only have 30 slices of cheese, so I can only make 30 grilled cheese sandwiches, and I'm going to have a bunch of leftover bread at the end. That's the idea between the limiting reagent and the excess reagent, right? I might have enough stuff. I might have enough bread to make 50 grilled cheese sandwiches, but I don't have enough cheese to make those grilled cheese sandwiches. So in this case, we would say that the bread is the excess reagent. I have extra bread that's going to be left over at the end. That's my excess. And we're going to say that cheese is our limiting reagent. I only have enough cheese to make 30 grilled cheese sandwiches. So obviously this is a really simple ratio. We were able to kind of do that math in our head. Today we are going to be looking at how to actually use stoichiometry to figure out what the limiting reagent is and figure out the excess reagent and how to put that into our calculation. So let's look at our definitions. If we were going to give the definition of a limiting reagent, I would just make it really simple. And I would say it's the reactant that is used up first. What am I going to run out of first? What that's going to do, the limiting reagent, is going to limit. It's going to limit the amount of product that I can actually make. So it's going to be limiting how many sandwiches or whatever product I'm trying to make in this case. When the limiting reagent or limiting reactant is used up, at that point, the chemical reaction stops. I've run out of one of the ingredients. I've run out of the one of the reactants. I can no longer make my product. So it's what determines where the stop is in my chemical reaction. So what we're going to do is we're going to go ahead and we're going to go right into an example. This example, you're going to find most of it is going to be stoichiometry. In fact, how we set up this example is going to be exactly like we set up stoichiometry in the last lesson with that chart there. So if you actually take a look, you've got a copy of this note. You've got a full PDF copy of this note where we've actually gone through and we've typed in all of the answers. So you might want to have that in front of you. I'm going to be going through and I'm going to be handwriting a lot of these. I think it's easier for you to follow along as I handwrite, because that way I'm really taking my time to explain what's happening. We also know that this stylus is a little glitchy though. So some of the numbers might be harder to read. That's okay, because you've got those numbers copied out, printed out, typed out in your note already. So the example that we're going to be looking at, we're not looking at grilled cheese sandwiches anymore. We are going to be looking at when we have 113 grams of aluminum. So that's one of our reactants. It's going to react with 279.5 grams of iron oxide. That's our other reactant. So it's asking what reactant is our limiting reagent and what mass of molten iron forms. So on the next slide, we're actually going to give you a chemical reaction, and we're going to show you how aluminum and how iron oxide will react to form molten iron. So we're going to have to answer two questions. The first thing we have to do is we have to find the limiting reagent. When we were looking at stoichiometry in our last lesson, you were only given one mass of a reactant, and you use that mass to determine the mass of product, right? We went from mass to moles, molar ratio, moles to mass. The only new difference that we're making here is we're giving you two masses, and you need to figure out which one to use. So we need to figure out, using these two masses, which one is a limiting reagent, and use that mass to go ahead and figure out the mass of our product. It's not as easy as actually seeing which one weighs less, because it actually doesn't matter for mass, it matters for moles. So we're going to use the same setup that we used last week. So first thing I'm going to do is I'm going to get rid of this video. Hi, it was lovely seeing you. So that way I can actually go ahead and write on the screen a little bit easier. So you're just going to listen to my voice. I'm going to pull my laptop towards me. I know the sound on these can go in and out a little bit. So the good news is I do have a microphone coming for next week. So you just got to listen to me the best that you can. And we are going to go ahead and we're going to take a look at our given values. So these were the two values that I was given in my question. I was given my mass of aluminum, and I was given my mass of of iron oxide in this case. So these are my two numbers that I was actually straight given to me in the question. The other thing that you are going to need is you are going to need the chemical reaction. So we're actually going to give you the chemical reaction in this case, and we're going to be going through and we're going to be completing this chemical reaction chart. It's the exact same chart that you used in our last lesson for stoichiometry. So you can see at the top of this chemical reaction chart is our actual reaction. We've got solid aluminum reacting with aluminum oxide, iron oxide, and it's giving you aluminum oxide, and it's giving you molten iron. So see that L symbol, liquid symbol right next to iron, Fe, that's telling us that we're dealing with molten iron. Remember, molten is just an example of a liquid. So what we are going to do is we need to make sure that this chemical reaction is balanced, right? Remember, that's not even a step. That's something that we got to make sure is done. So I'm going to go ahead, I'm going to take a look. I'm going to see that this chemical reaction is actually not balanced. So I'm going to go ahead and I'm going to balance my chemical reaction. So if you take a look on this chart, now I've gone through and I've balanced my chemical reaction. It's really important that you do that to start, because those coefficients are going to be really important for our molar ratio step. Now I'm actually going to go ahead and I'm going to start recording information into this chart. So I'm going to record my mass of aluminum that was given to me. That was 113 grams. I'm going to record my mass of aluminum oxide that was given to me. That was 229, right? Can't read my own handwriting. 279. Good thing I checked. That was 279.5 grams. So we've been given two different reactants. In this case, we need to figure out which one is the limiting. So we're going to go ahead and we're going to find the molar masses for each of these. The molar mass for aluminum is actually really easy. It's the same as the molar mass that's listed on the periodic table. So we can just go ahead and record that at face value. That's going to be 26.982, and that's going to be in grams per mole. My molar mass for iron oxide is a little bit trickier because it's actually a compound. So to figure out my molar mass of iron oxide, I'm going to have to take the molar mass of iron and times it by 2. Why am I multiplying it by 2? Because I have 2 irons. I'm then going to add to it my molar mass of oxygen, but I'm going to multiply that by 3. Why am I multiplying it by 3? Because I have 3 oxygens. So if I look at the periodic table, my molar mass of iron is 55.84 0.45. And if I look at the periodic table, my molar mass of oxygen is 15.999. So I'm going to go ahead, I'm going to sub those in, I'm going to add them together, and you're going to get a grand total of, if you do that calculation on your own, it's going to be 159.687 grams per mole. So this is something we started doing week 1. If you're not sure how we got that number, go ahead, pause the video, and the full transcript of this, you do have a copy of it in the PDF. Last thing I'm going to do while I'm here, while I've got my periodic table in front of me, is I'm going to calculate my molar mass of my product. Because remember, in the end, I am going to need that as well to figure out my mass. So I was given the mass of 2 reactants. So my mass of aluminum oxide, or aluminum, my mass of iron oxide. And if I go back and read the question, part of the question is asking me how much molten iron is going to be produced. So at the very end, my last step, I'm going to be looking for molten iron. So while I'm here, I might as well figure out my molar mass of that as well too. So I'm going to look at the periodic table, and on the periodic table, it says that my molar mass of iron is 55.845 grams per mole. All right, now that I've got that, I can go ahead and I can move on to my next step. And in my next step, I'm calculating my number of moles that have been made per reactant. I'm going to go ahead and in this little margin here, I'm going to zoom in a little bit. And in this margin here, I'm going to remind you of the formula to figure out number of moles. Number of moles is just going to be equal to our mass, little m, divided by our molar mass. Well, if you take a look at our 2 columns on top of this, I've actually been given mass, and I've actually gone through and calculated molar mass. So I've got those 2 numbers. So I'm going to start by figuring out the number of moles of aluminum here. So my number of moles of aluminum is going to be my mass. Well, in this case, my mass is 113. I'm going to divide it by my molar mass. That molar mass, 26.982. Now, just to save space, because this column is so low, or so small, I'm not going to include units in this. But again, if you look at this transcript later, if you pause this video and look at the transcript, it actually shows you how to go ahead and cancel out your units. So since you're going to have space on your piece of paper, please make sure that you are including your units in your calculation, because it's a great way to make sure you're dividing your numbers properly. It's a great way to make sure that you're doing the proper calculations, because your units are always going to cancel out in the end. So if I take 113 and divide it by 26.928, it's going to give me a grand total of we're going to call it 11188. I'm going to keep 3 decimal places because in my molar mass, I had 3 decimal places. Unit for that is going to be in grams. All right, next up, we're going to look at how to figure out our number of moles of iron oxide. So again, number of moles is equal to mass divided by molar mass. My mass of iron oxide was 279.5. And my molar mass in this case was 159.687. If I go ahead and I plug that into my calculator, I'm going to get a grand total of 1.750 grams. All right, so we've gone ahead and we've converted from mass to number of moles. So now you would think that we can just look and figure out which one we have less of. But there is one other consideration that we have to make. Think back to our grilled cheese example. Think back to our ratio of our grilled cheese sandwich. To make a proper grilled cheese sandwich, we had 2 pieces of bread for every 1 piece of cheese. So it's not enough to consider the number of moles. We also have to consider the ratio. Maybe my recipe requires that I'm using more of these than the other. So I have to go ahead and use that molar ratio. The good news is that that molar ratio, how we set it up in stoichiometry, we're going to set it up the exact same way here. And we're going to use our molar reaction chart. So let's start by looking at our first column. I'm going to scroll up so you can see it. Remember, we're dealing with aluminum. So we're starting with aluminum. So I'm going to go ahead and I'm going to record my number of moles of aluminum. Where am I getting this number from? It's my value that I just calculated in the chart above. So normally I would write down 4.18 mole aluminum, right? Keep the proper unit. Again, to save space in this little chart, I'm not going to write that. But if you look at the full transcript, you can see how these units are going to go ahead and cancel out. Next thing I need to consider is the number of moles that I'm looking for. I'm going to call that X. And what am I looking for? What product is it asking about? It's asking about molten iron. So I'm just going to call that Fe in this case. Now, it's important that I use my coefficients from that balanced chemical reaction. So I'm going to go back to my chemical reaction, and I'm going to see what number is in front of aluminum. It's a 2. And then I'm also going to take a look and see what number is in front of iron. It's also a 2. So I'm going to record 2 for aluminum, and I'm going to record 2 for iron. Remember to keep your elements in the same. Both aluminums are on the top and both irons are in the bottom. Now I'm going to go through and I'm going to cross multiply. So X, Fe. And remember, cross multiplying means I'm multiplying by whatever is across from it. So I'm going to multiply that XFE by 2Al. That's going to be equal to 4.188 Al. And I'm going to multiply that by 2Fe. Now I want to go ahead and get this X by itself. To get this X by itself, I need to take 2Al and I need to divide. That's going to look like this. Oh, we're doing so good. We're doing so good with the glitches. All right, so I've got 4.188 Al times 2 Fe, that's an Fe, all divided by 2Al. If I've done this right, these are going to go ahead, these are going to cancel out, so this Al is going to cancel out, this Al is going to be canceling out, and I'm going to be left with just Fe. So I want to take 4.188 times 2 divided by 2, punch it into my calculator, and I'm going to find that the number that I get is actually going to be 4.188 moles of Fe. I want to point out something. This is exactly where we started. We started with 4.188 and we're ending with 4.188. A lot of you that are really great at math were yelling at me when I first set up this ratio. Take a look here. 2Al, 2Fe. We call that in math a 1-to-1 ratio. Those numbers are the same. If you ever see that, if you see a 1-to-1 ratio, you're going to end up with the exact same number of moles. So you can actually skip that middle step if you want. If you're worried about remembering that, if you think it's going to be too much to remember, don't worry. You can always do that ratio, and that ratio is always going to work. But if those numbers are ever the same, it's a 1-to-1 ratio, so we're going to end up with the exact same number of moles. All right, we have to do the exact same for iron oxide. Good news, it's great practice for ratios. You're going to be really good at this, right? So let's take a look at iron oxide. So how many moles of iron oxide did I have? Oh, geez. You guys didn't even correct me before. Look at this. Right? I just caught that. So remember, number of moles, the unit for that is going to be moles. Hopefully you caught that. It's a great test if you're paying attention. All right, so let's take a look at how many moles of iron oxide I had. I had 1.75 moles. And I'm going to write down iron oxide. just to remind me what chemical I'm dealing with. And I'm again looking for molten iron. So it's the same product that I'm looking for. So I have to look at my balanced chemical reaction and I need to see what numbers are in front. So I'm going to take a look at the number in front of iron oxide. There's no number written, so we go ahead and assume it's a 1. And I'm going to take a look at in front of my number in front of iron, and there is a 2 written there, so I'm going to record a 2. So I had a 1 in front of my iron oxide, and I had a 2 in front of my iron. Now take a look, these are two different numbers. It's not a 1-to-1 ratio, so we are going to have to go through and figure out that cross multiplying. So XFE, I'm going to multiply it by whatever it's across from. So that's going to be 1 Fe2O3. That's going to be equal to 1.750 Fe2O3 multiplied by 2 Fe. I now want to get my Fe by itself. So in order to get Fe by itself, I need to divide by Fe2O3. So it's going to look like this. Those Fe2O3s are going to go ahead and they're going to cancel out. So all that I'm going to be left with is 1.75 times 2. So I'm going to find that I have 3.501 moles of iron. All right, that is a lot of math. And remember, my whole goal here was to figure out what my limiting reagent is. So remember, a limiting reagent is going to be whatever I run out of. So which one is going to limit my reaction? Which one am I going to run out of first? So I'm going to take a look, and I see that here I have 4.188. Here I only have 3.501. So I'm going to find that I'm going to run out of this one first. So therefore, this is my limiting reagent. So I'm going to go ahead and I'm going to record limiting reagent is, what is it? Well, let's scroll back up and let's find out. My limiting reagent in that column was Fe2O3. So in this case, therefore, my limiting reagent is going to be equal to Fe2O3. How did I know that? I'm going to run out of that first. All right, the nice news with figuring out limiting reagent this way is we've already done about 95% of the work for the question. So the question was asking us two things. It was asking what my limiting reagent is. I figured that out. And it was also asking us the mass of the molten lava that you are going to create. So if you take a look here, my last step is going to be my mass after my reaction. I'm just going to remind you of the formula for mass. This is from stoichiometry in our last lesson. Mass is equal to the number of moles times the molar mass. Well, do we know the number of moles of iron that's going to be created? Absolutely. We just figured that out. Do we know the molar mass of iron? Yes, we figured that out in the very first step. So we actually only have one more calculation to go. Now, I'm going to ask you to be very careful here because remember, our whole goal of figuring out the limiting reagent is to use that to calculate our amount of iron. So be very careful here that you're using your limiting reagent. Our limiting reagent was here. So when I do this calculation, when I go to figure out my mass, I'm going to use my number of moles associated with iron. That's 3.501 moles of iron. I'm going to multiply that by my molar mass of iron. I'm going to scroll up here. I'm going to remind you, you figured out your molar mass of iron at the very beginning. So I'm going to multiply that by my molar mass of iron. That was 55.845. And I'm going to find that my mass is going to be worked out to 195.49 grams. So therefore, my mass of molten iron is going to be equal to 195.49 grams. If you had used your excess reagent, if you had used aluminum in this case instead, you would have got a number that's too big, right? You can't make that much based off the aluminum that you have because you're going to have leftover aluminum at the end. So make sure that you are using your limiting reaction. Okay, not too bad, right? So it's pretty much the exact same as last lesson, except you're doing everything twice. So again, if you had a hard time reading these numbers, I agree, pen is not great. Or if you want to look at how to calculate or how to cross out units, go ahead and take a look at the transcript. For those of you that are great and get it, you can hit pause now and try the next example yourself. For those of you that are still struggling a little bit, we are going to try another example. So I'm going to zoom out. This is that entire transcript I was talking about. Look at it, it's so nice. It's typed out for you. You can see all the numbers. It's a great way to go through and make sure that you know what we're talking about. And let's take a look at our next example. And our next example is going to be here. So let's just go through and let's highlight what we've been given. So we've been given our chemical formula. And notice we've actually been given our balanced chemical formula, which is nice. So we can go ahead and make sure it's already balanced for us, so we don't have to do that. We've also been given two different masses. So we've been given a mass of aluminum, and we've also been given a mass of oxygen. So again, we've been given the mass of both reactants. We need to figure out which one is the limiting reagent, and then we need to figure out, using the limiting reagent, how much aluminum oxide is going to be produced. So we're going to set this up the exact same way we did last time using a reaction table. So notice that we've put the balanced chemical reaction at the top, and the first little bit of this table is just recording all the information that we've been given. So in the question, we were given the mass of aluminum, 134.9 grams. We were also given the mass of oxygen, 96 grams. We need to calculate the molar masses. Molar mass of aluminum is just straight from the periodic table. So molar mass of aluminum is going to be 26.982 grams per mole. Molar mass of oxygen is a little bit more challenging. To figure out the molar mass of oxygen, we want to take the molar mass of oxygen and want to multiply it by 2. Why are we multiplying it by 2? It's O2. There's that small subscript of 2. So the molar mass of oxygen is 15.999. If we multiply that by 2, we're going to get the molar mass of oxygen is going to be 31.998 grams per mole. While we're here, we might as well figure out the molar mass of aluminum oxide. Why do we need the molar mass of aluminum oxide? Because in that very last step, we're going to need that molar mass to figure out the mass of our product. So to figure out my molar mass of aluminum oxide, I'm going to take my molar mass of aluminum and multiply it by 2. Why 2? Because I have 2 aluminums. And I'm going to add to that my molar mass of oxygen, and I'm going to multiply that by 3. Why 3? Because I have 3 oxygens. So if you actually go through and do that, you are going to find a grand total of 101.961 grams per mole. If you're confused at how we got this number, go ahead, stop that video, take a look at that PDF transcript, and it'll walk you through that in a little bit more detail. All right, our next step is we need to figure out number of moles. We don't know which one is our limiting reagent, so we're going to have to do it for both. Just a reminder, the formula for number of moles, mass divided by molar mass. So I'm going to start here with aluminum, and I'm going to take the mass of aluminum. That's 134.9. and I'm going to divide by that molar mass, 26.982. Again, I am taking a shortcut. I'm not including the units. When you do this, please make sure you include the units. I'm going to work that out to 4.9996. I'm going to keep an extra decimal this time, just so we don't have to round that 9. And the unit for this is moles. Look I didn't mess up this time. So it's moles, not grams. Next up, let's figure out our number of moles of oxygen. So number of moles is going to be mass divided by molar mass. That's going to be 96. I'm going to divide that by my molar mass, so 31.998. If I go ahead and divide those two numbers, I'm going to find 3.000 moles. All right, so now I've converted to moles. My next step after mass to moles is going to be that molar ratio. Again, I don't know which one is my limiting reagent yet, so I'm going to have to do it for both. So I'm going to start with my number of moles of aluminum. So I've got 4.9996 moles of aluminum. And I don't know yet how many moles of aluminum oxide I have. So I'm going to keep that as X, and that's what I'm going to try to solve for. Now, in my next little section here, my next part of the ratio, I need to look at the coefficients in my balanced chemical equation to figure it out. So I'm going to scroll up. I'm going to take a look at the number that's in front of aluminum. It's a 4. So I'm going to write 4 here. And then I'm going to scroll up and I'm going to take a look at the number that's in front of aluminum oxide. It's a 2. All right, they are not the same. It's not a 1-to-1 ratio. So I'm going to have to go through and cross multiply. So I've got X aluminum oxides, and I'm going to multiply that by what it's across from. That's aluminum. So I'm going to multiply that by 4Al. That's going to be equal to 4.9996 Al times 2Al2O3. Next step, get X by itself. To get X by itself, I'm going to have to divide by 4 aluminums. So again, if I do this right, these are going to go through and these are going to cancel out. So aluminum, cancel out. Aluminum, cancel out. I'm going to be left with aluminum oxide. If I go ahead and plug that into my calculator, 4.996 times 2 divided by 4, I'm going to get 2.4998 moles of aluminum oxide. All right, let's do the exact same thing for oxygen. So we're going to go ahead and set up our ratio for oxygen. I'm actually going to do it kind of to the right here. I'm running out of room real fast. That's okay. So I'm going to take a look at my number of moles of oxygen. That's from my column above. So for oxygen, I had 3.000 moles of O2. I don't know the number of moles of aluminum oxide, so I'm just going to call that X. All right, I'm going to look at my balanced chemical equation. I'm going to use my coefficients. So in this case, if I scroll up, there is a 3 in front of oxygen. No, so notice both the oxygens are on the top. Aluminum oxide is going to be on the bottom here. So if I take a look, I see a 2 in front of aluminum oxide. It is not a 1-to-1 ratio, so I'm going to have to cross multiply. So X going to multiply that by what's across from it. That's oxygen. Right, so we got that from here. That's going to be equal to 2. All right, so next up, we're going to go ahead and we are going to try to get X by itself. To get X by itself, we're going to have to get rid of that 3O2 by dividing. So we're going to have 3O2 times 2Al2O3. Divide that all by 3O2. If I do this correctly, my O2s are going to cancel out, and that's going to leave me just with aluminum oxides. So if I go ahead and I punch that into my calculator, 3 times 2 divided by 3, you're going to find that I'm going to end up with a total number of 2 moles of aluminum oxide. So we can actually go ahead and answer the first part of the question right here. And the first part of the question was, what's my limiting reagent? Remember, my limiting reagent is whatever I'm going to run out of. So if I take a look at my final number for aluminum, I have 2.4998, right? That's right here. And if I take a look at my final number for oxygen, it's just 2. So which one am I going to run out of first? My number that's associated with oxygen. How did I know this? Because it was my lower number. So therefore, my limiting reagent is oxygen. How did I know that? Run out of it first. So I'm now going to use oxygen as my limiting reagent, and I can go ahead right to my last step, right? I've already done most of the work already. So my last step is going to be to figure out how much aluminum oxide that oxygen is going to create. So this is my last step in my organizer here. And in order to go back to mass, my formula for mass is number of moles times molar mass. So I'm going to take my number of moles, I'm going to take my molar mass, and I'm going to figure out the mass of aluminum oxide that I have. Be very careful to use your number of moles from your limiting reagent. So my number of moles from my limiting reagent is here. It's my smaller number, it's 2. So my mass is going to be equal to 2 moles. I need my molar mass, and I need my molar mass of aluminum oxide. Well, I actually already calculated that at the very beginning. It's 101.961. So my molar mass here, I've gone ahead and I've included the units, so you can see they're going to cancel out. And my mass is going to be left with 2 times 101.961. That's going to give me a grand total of 203.93 grams. So overall, therefore, oxygen was a limiting reagent, and it will produce 203.93 grams of what was our product? Aluminum oxide. All right, you have homework questions. Please make sure that you practice your homework questions. And also, I don't know about you, I am hungry. I am going to go make myself a grilled cheese sandwich. All right, tune in next week and we'll be looking at wrapping up this unit. See you later, guys. Bye. Have a good day.